Today we're going to talk about using the method of undetermined coefficients when we have a higher order, meaning higher than second order, which we've looked at in the past. We have a higher order linear constant coefficient differential equation. The method really is not changed much, not changed virtually at all, since we were looking at it with second order linear constant coefficient differential equations. So all I want to do is show you a few examples to show you how things can feel a bit different, but we're really just applying the exact same principles. Let's say we want to solve this fourth order differential equation. The fourth derivative of y minus twice the third derivative of y plus the second derivative of y equals t squared plus 1. Now, of course, the first thing we'll do is solve the homogeneous equation. And that has characteristic equation, which is r to the fourth minus 2r cubed plus r squared equals 0. Now we want to factor this. And again, when solving higher order linear constant coefficient homogeneous differential equations, this factorization might be the most difficult thing. Here it's actually pretty easy because we can just factor out an r squared. And what we're left with is r squared minus 2r plus 1. And we can factor that as r squared times r minus 1 squared equals 0. In other words, the roots are just 0 and 1, and both have multiplicity 2. So what does that tell us about solutions? y1 we can take as e to the 0t for that r equals 0 root. That's just the constant function 1, which you can see immediately is a valid solution. But because we have the 0 is a multiplicity 2, we also have y2 equals t e to the 0t, which is just t. And again, you can plug this in your head very quickly and see that that's also a legitimate solution. We can pick y3 to be e to the t. That's because r equals 1 is a root. Again, it's pretty easy to check in your head that that's a good solution. Slightly more complicated is to check that y4 equals t e to the t is also a root, and we know that because this r equals 1 is a root of multiplicity 2 in this equation. So we have now 4 solutions. They're independent. Their Wronskian will be non-zero. This will give us the complete general solution to the homogeneous equation, which we'll write down later. Let's now look for a solution to the non-homogeneous equation. What should we guess as our solution? Well, we first might want to try a particular solution, y of t. Because we have a polynomial of degree 2 here, we might want to try at squared plus bt plus c for some unknown coefficients a, b, and c. Well, this isn't going to work. The reason it's not going to work is because we already know that 1 and t, here and here, these are solutions to the homogeneous equation. And when we have any interference with the solution of the homogeneous equation, you'll see this would just be the same as choosing y of t equals at squared, because the bt plus c will all zero out on the left side. And in general, and in this case as well, that will not be sufficient in order to allow us to choose a to make things work. So what do? We multiply. This doesn't work because of interference. What do? We try something else. We try to multiply everything by t. So we could try at cubed plus bt squared plus ct. Multiply the whole thing by t. And this still won't work because the ct is still has interference with the solution y2 equals t. So we still don't have enough degrees of freedom here to make things work. So we multiply by t again. And you can probably see in your head, you don't necessarily have to write these down, but this is the idea that both of these don't work because of interference here with 2 terms, now with just 1 term. But now we try y of t equals a t to the fourth plus bt cubed plus ct squared. That's just t squared times our original guess. And this will work. You can check for yourself that when you take 4 derivatives, this part all disappears and you end up with 24 a for the 4th derivative. Y cubed would just be, oh, not y cubed, y triple prime, I mean. Y triple prime is, what do we get here? If we just differentiate 3 times, we get 24at plus 6b. I'm doing this kind of backwards. You probably would want to compute y double prime first. Y double prime, computing twice, we'll get 12at squared plus 6bt, and now we'll have 2c. And when you put these all back into the original differential equation, you get the 4th derivative of y minus twice the 3rd derivative will be 24a minus twice 24at plus 6b plus the 2nd derivative, which is 12at squared plus 6bt plus 2c. This must equal t squared plus 1. How do we find our coefficients? We'll gather terms with t squared. Here we have 12at squared, and that has to be 1 times t squared. So 12a must equal 1. We want to solve this system. 12, I didn't write that correctly. 12a equals 1. If we match coefficients on t, here we have minus 48 at. Here I have 6bt, and that has to be 0. And finally, if we match constant terms, here we have the constant term 24a, and then here we have the constant term minus 12b, and then here we have the constant term plus 2c, and that must be equal to the constant term here, which is 1. We want to solve this system of 3 equations in 3 unknowns. How can we do that? Well, I've done that ahead of time, and unless I've lost my solution, well, here's what we get. Immediately here we can see that a must be 1/12. From this equation here, we can tell b must be 2/3, because this is minus 4, and then we need b to be 2/3 to get plus 4 to equal 0. And once you have a equals a 12th and b equals 2/3, this last equation tells you that c must be 7/2. And what does that tell us about our solution? It tells us, I'll write it up here, y of t must be exactly 1/12 t to the 4th plus 2/3 t cubed plus 7/2 t squared. And thus the general solution is y of t equals a constant c1 times 1 plus c2 times t plus c3 times e to the t plus c4 times t e to the t plus our particular solution 1/12 t to the 4th plus 2/3 t cubed plus 7/2 t squared. And this is for any real numbers, c1, c2, c3, and C4. Piece of cake. Let's go through one more example. Try to be quicker with this one. How do we solve y triple prime minus y double prime plus y prime minus y equals sine t? Again, we first solve the homogeneous. Which has characteristic equation r cubed minus r squared plus r minus 1 equals 0. Now this one might be trickier to factor. How can we actually factor this easily? You could just guess r equals 1 is a solution and see in your head that it is. Remember, a nice rule is that when you have a monic polynomial here, if you want an integer solution, or in fact any rational solution, it will have to be an integer, and that integer will have to be a divisor of the constant term, which is -1. So only plus and minus 1, those are the only possible rational solutions, and if you check r equals 1, you'll see that it works. That means we can factor this as r minus 1 times something. You could use polynomial division if you have to, and you'll see pretty quickly that this factors as r minus 1 times r squared plus 1 equals 0. Now, what do you do if there's no integer root? Well, in general, you might not be able to get a nice factorization like this. You might have to use a cubic formula, which again, nobody knows. Not that literally nobody knows. You could Google it and you can find the cubic formula, but we don't teach anybody that. It's not part of any of our math classes. So virtually nobody ever learns the cubic formula, and it's very hard to deal with. So it can be a very tough problem. But luckily, here things work out nicely. So what are the solutions? R equals 1 from this linear term, and r squared plus 1 can factor into r plus I times r minus I. In other words, r equals I and r equals minus I are solutions. What does that tell us about solutions to the homogeneous differential equation? We get solution y1, which is e to the t, and for y2 and y3, those come from this conjugate pair of non-real solutions. And since these are 0 plus I and 0 minus I, we can get e to the 0t times cosine of t, which is just cosine of t, and e to the 0t sine t, which is just sine t. So we get these three solutions. Again, these are very easy to check that the Wronskian of those three is non-zero. They constitute a fundamental set of solutions. And the complete general solution to the homogeneous equation is the set of all linear combinations of these. I'll write that down later. How do we find a particular solution to the non-homogeneous equation? That's to this equation up here. Well, we might try a solution of what form? We have a sine t here. In general, guessing a multiple of sine t won't quite work because we'll get cosine t's here for the first and the third derivatives. So the general thing we would start by trying to guess is a sine t plus b, or let me actually write it in the form that I'm used to, a cosine t plus b sine t. It doesn't matter which way you write that, of course. But this won't work because there's interference, the cosine and sine, with the solutions to the homogeneous. If I tried a function like that, the left side would be identically 0, and there's no way by any choice of constants a and b I would get that to equal sine t. So instead, I'll try y of t to be this thing multiplied by t, which we can write as at cosine t plus bt sine t. And I'll leave the details to you, but when you try this, compute y prime, y double prime, and y triple prime, which can be a bit of a mess. Trust me, I ran through this on a piece of paper at home. You write out what the left side is equal to and set it equal to sine t, and of course think at the end that'll be sine t plus 0 times cosine t, and solve for a and the constants a and b. You find a is 1/4 and b is minus 1/4. Actually works. In other words, a particular solution is 1/4 t cosine t plus, 1/4 t cosine t minus 1/4 t sine t. And thus our general solution to the non-homogeneous equation is y of t equals c1 e to the t plus c2 cosine t plus c3 sine t plus our particular solution 1/4 t cosine t minus 1/4 t sine t. And this will work for any real numbers c1, c2, and c3.